Welcome to part 1 on unique logarithmic behavior. In this section, we will look at the laws of logarithms and the change of base formula. Let's start with the law of logarithms. Since logarithms are exponents and they're just written in a little different format, the laws of exponents give rise to the laws of logarithms. Keep in mind that arithmetic with logarithms is always one level down on the order of operations. And if you're not quite clear on the order of operations, maybe it's been a little while, PEMDAS might ring a bell. It's PEM stands for parentheses, exponents, multiplication, division, addition, subtraction. So multiplication becomes addition. If we were going to write this in just shorthand, multiplication times goes to addition. So see how we have a times b inside the log base a of ab. When we expand it, so this is the compressed version, the consolidated version. This is the expanded version, log base a of a plus log base a of b. Division goes to subtraction. So again, this should sound similar to the rules for exponents, and that's exactly what logarithms are. They behave with a similar trend, I guess, as an exponent. So if you have log base a of capital A over capital B, then you get log base a of a minus log base a of b. Notice that the denominator becomes a negative term. And then finally we have exponentials, or exponentiation becomes multiplication. So if you think of this, the e represents exponential and it goes to one level down, multiplication. So exponentials, I'm trying to think how to write this. Let's just say a number raised to an exponent goes to multiplication. So you can see that with this exponent c on log base a of capital A raised to the c, you can bring that down front and you'll have a c times the logarithm base a of capital A. So let's give this a try now that we've talked about the rules. Let's give these examples a try. It says to evaluate each expression without a calculator. So we have log base 6 of 18 plus log base 6 of 12. We can rewrite this as log base 6, since the bases match on both these logarithms, we can combine them. And notice that we are compressing the logarithm into one term. So we can use multiplication. So we would have 18 times 12. And we might not know what this is, so we can say equals x, because we're not sure exactly what it is. So if I multiply 18 times 12, I happen to know that that is log base 6 of 216. And if that's the case, I can say 6 raised to the x is equal to 216. Well, 216 is a perfect cube, and it just happens to be the perfect cube of 6. So I can say that 6 to the x is equal to 6 to the third, and therefore x equals 3. Now let's take a look at the next example. We've got log base 2 of 80 minus log base 2 of 5. So we'll rewrite this. The negative term means that we're going to put the 5 that's inside the logarithm in the denominator. Our bases match, so we can do this. We can combine the logarithms. So we're going to rewrite this as log base 2 of 80 divided by 5. And we're not sure what this equals, so we'll say it equals x. Then I simplify 80 divided by 5. So I'll have log base 2 of 16 equals x. So I can say 2 raised to the x equals 16. So 2 raised to the x equals 2 times 2 is 4, times 2 is 8, times 2 is 16. So 2 to the 4th. Therefore, x equals 4. Let's take a look at the last example in this set. We have a negative 3 times log base 5 of 1/5. I'm going to rewrite this as log base 5 of 1/5 raised to the negative 3, because I can bring this power back up if I'm trying to figure out what it means. There are multiple ways to write the logarithm. So I will have log base 5 of 5 raised to the positive 3. I can rewrite it that way, which is very convenient because now I need to figure out what it equals. So we'll say it equals x because I'm not sure yet. 5 to the x equals 5 to the third. So we can say 5 to the x equals 5 to the third. Therefore, x equals 3. We're now going to switch gears just a little bit. We're going to use the laws of logarithms to write each expression as the sum or difference of logarithmic functions containing no exponents. So when we're all done, we shouldn't have any exponents. We are expanding the logarithm. We are not consolidating it. Before, we were identifying the value. Now, we're using the laws to expand it and not have any exponents. I have log base 2 of 5, x to the third, y. I'm going to first break the different logarithms apart because of multiplication. So multiplication now becomes addition. So I have log base 2 of 5 plus log base 2 of x cubed plus log base 2 of y. And I'll go ahead and put this 5x to the third and y in parentheses so you can kind of see what is inside the log and what is not. Next, I will use the exponent rule that becomes multiplication to bring the 3 on the x cubed out front. And I'll rewrite it in its final form. I will have log base 2 of 5 plus 3 log base 2 of x plus log base 2 of y. And I'm done. I've expanded it. There are no exponents. And it is a sum or difference. Next, let's look at log of, and notice it's not given what base it is, so it's assumed to be 10. Log base 10, you don't have to read it that way, but log of x plus 1 over the cube root of x. For clarification purposes, I'm going to rewrite this cube root of x in the denominator as x to the 1/3. So I'll have log of x plus 1 in the numerator over x to the 1/3 in the denominator. Now remember, when you have division, you subtract the portion in the denominator when you turn it into its own separate term. So the denominator will be the log of x to the 1/3, and the numerator will be a positive x plus 1. I'll show you what I mean here. So we can rewrite this as log of x plus 1 in the numerator and then minus, because this is the portion that was in the denominator, so minus log of x to the 1/3. Now I'm going to rewrite the whole thing with no exponents because I need to bring that 1/3 out front. So I will have log of x plus 1 minus 1/3 log of x. And you might be asking yourself, now, hey, what about this x plus 1 in here? Can I do anything else with this x plus 1? Do I break it apart further? And the answer is no. And the reason it's no is because this is addition. And notice that addition is at the end of the order of operation. Addition, subtraction, that's at the end of your order of operations. So there are no lower orders down from addition, so stop here. Let's look at C, the last example. We have the natural log of e raised to the 0.03x plus log of 10 raised to the x. Now this one is just meant to see if you were paying attention when we were looking at a previous section on the rules of logarithms and natural logs. Because remember, if you have an exponent, you can bring it out front, so we'll do that first. We'll have 0.03x times the natural log of e plus x times log of 10. Well, if you may recall, natural log of e is equal to 1, and log base 10 of 10, assumed to be base 10 because it's not listed, goes to 1. These both go to 1. And so I will have 0.03x plus x. And so I can say that this simplifies, and remember this is a 1x here, this simplifies to 1.03x. If I knew what x was, I could give you an actual value, but for now we'll call this good.